Sudhanshu Shekhar Tiwari, Assistant Professor, School of Forensic Science and Risk Management. I invite you all to the first webinar of the first dialogue webinar series. Today we have with us Dr. Rajesh Verma, Deputy Director, Regional Forensic Science Laboratory, Mandi, Himachal Pradesh, India. And he will be discussing with us importance of statistics in forensic science. We also have with us Dr. Ranjit Singh from SIFS, New Delhi. And I would like to request, sir, if you kindly introduce Dr. Rajesh Verma, our invited expert, to the audience. Thank you.
Thank you, Sudhanshu. So, good evening, all. Thank you, Rajesh Verma, sir, for accepting our invitation to give a talk on importance of statistics and the forensic sciences. So, we all welcome you for this 3 days webinar. So, sir need no introduction, but as a formality, I had to give the introduction of the sir. Dr. Rajesh Verma is a Deputy Director of the Regional Forensic Science Laboratory at Mandi, Himachal Pradesh. He has a doctorate degree in physics from IIT Roorkee. He is into research since early 90s and has over 30 years of experience in research and analytical work. He has published and presented over 30 papers in various international and the national journal of review and various conferences. He joined forensic profession in year 2000 as an assistant director and headed the physics and ballistic division of the State Forensic Science Laboratory in Himachal Pradesh. After working for about 11 years as assistant director, he was selected to head the Regional Forensic Science Laboratory at Mandi as a deputy director. In addition to his administrative duties, Dr. Verma has pursued his interest in research and interest in statistics and its applications to forensic sciences. He has developed an understanding of the various issues in forensic science and is keen on using statistics and the computer to improve the practice. He has also been using his capabilities in the development of the automatic speaker identification and the facial identification systems. He is currently engaged in development of the state-of-the-art multimedia forensic facilities in the Himachal Pradesh with the collaboration of IIT Mandi and was instrumental in signing of an MOU for collaborative research between RFSL Mandi and the IIT Mandi. So, thank you, sir. Once again, we welcome from the Raksha Shakti University. So, now I'll request you to share your knowledge with the participant.
Thank you, Dr. Ranjit Singh. And I'm also thankful to Raksha Shakti University for giving me an opportunity to share my experiences about the application of statistics in forensic science. This will be a 3-part webinar. We'll continue for the next 3 days. And I have tried to pack a lot of information in these webinars, and keeping in view that a lot of students will also be there. I have tried to introduce the basics of statistics as it applies to forensic science. At the same time, this webinar will also be useful for practitioners in forensic science who may be new to the use of statistics in forensic science. So, and I just want to mention that my interest in statistics goes back to the year 2011, when I became relatively free from the expert jobs, and the work here was more of administrative nature. So I could find time to pursue my interest in research, and also found a new interest in statistics and its application. As you all know, statistics is now very popular in the world, and most of the applications are there of statistics in forensic science. And there have also been some review of the international practice of forensic science, and I will also discuss these reviews. And I'm here to share my experiences and my efforts with you to apply statistics in forensic science. So I start with my presentation. The first presentation will be, just a minute, please. So this first session is about uncertainty in forensic science and the importance of statistics. This session will have two sections. One will be covering the uncertainty in scientific evidence and the recent developments in the forensic professional practice. And then I will also touch upon the different kinds of biases. Then we'll talk about the Innocence Project. And then we will see how statistics can be used in forensic science and evaluation of evidence and the calculation of likelihood ratios. After this introduction, we will take up the basic of statistics. And we will go on discussing the samples, population, and variables. We will also discuss the association between variables. We will define probability. And then we will introduce hypothesis testing using a case study. This case study I have been using for my various lectures. And it is taken from some open source book. It's called Open Intro Statistics. And you can also go for this book and see the various presentations and the material there. So when we talk about forensic science is basically the scientific examination of physical evidence. And right from the crime scene, where the physical evidence is gathered, to the courts, where this physical evidence is presented as evidence and interpreted, and the strength of evidence is evaluated. Based on this interpretation, the verdict is pronounced. You see that there is uncertainty involved in all these stages of scientific evidence collection and evaluation. First, at the crime scene, the production of physical evidence is accidental, as it is not premeditated and does not occur under controlled conditions. So it is random and accidental. And further, the transfer or impression of the materials at the scene or from the scene, their persistence, their location, and their quantity and quality are also not planned. It is again random. And uncertainty is also involved during the examination and preparation of the results of evidence in the laboratory. Even during a trial in the court of law, the verdict is given based on the evidence that is presented, and that is admissible. So if you talk about the crime scene, there are so many factors that influence the amount of physical evidence, including the intensity of the alleged contact, and the evidence is also circumstantial. And then one should know that when a forensic scientist gives opinion about the evidence, then he cannot be absolutely confident, or absolutely certain about one item having some common origin with another item from the physical evidence, because simply the fact that he was not there, this evidence is all circumstances, so he cannot be absolutely certain about his opinion. And then there is another factor, that evidence is searched, recovered, and collected some time after the event, not immediately, and also this collection depends on the ability of the crime scene investigator to understand, recognize the evidence, and recognize its importance. Therefore, this implies that the evidence provides information with a given probability. We cannot be certain, but we can only give probable opinion about the physical evidence. And we use a particular degree of certainty when we talk about the association of the physical evidence with that from the crime scene. And then further uncertainty is involved in the laboratory, where methodologies are chosen because of their discriminating abilities, and they are intended to detect features that are variable. And it's also desirable that they provide a high degree of sensitivity, meaning that they can detect and distinguish features at the lowest limits. In terms of detection, they are also supposed to detect correctly and in a manner that different examiners will reach the same findings. This is a very important factor to be kept in mind during laboratory examination. That is, the examination and the documentation in the laboratory should be thorough, and the opinion arrived should be based upon based upon solid grounds, and this opinion forming should be objective. That is, if two examiners of the same qualification and same experience are there, they should be able to frame the similar opinion. But these things cannot be granted with absolute proof of certainty. And further, the forensic laboratory examinations are comparative in nature and involve the comparison of features. Please keep in mind that what I am going to discuss in the next 3 sessions is applicable to the identification sciences. That is where the comparison of features is involved. Like it may be firearms, shoe prints, or hair, or fibers, where we compare the features. And then the examiner looks at similarities as well as dissimilarities and will determine whether or not she can differentiate the two items. That is, the focus is not on comparing the similar features only. If features compare well, it should not be focused. We should also note down the dissimilarities. And only when the dissimilarities are not significant, then we can say that these two items compare well. We should take into account the similarities as well as dissimilarities. And then the examiner can also be able to describe, should also be able to describe his confidence in declaring the so-called match between two sets of items. I have mentioned so-called match. In fact, I understand that there is nothing as match or no match. We'll come to this later on. And here this slide says that it's crucial to understand the contribution of scientific evidence does not offer a proof of absolute certainty to any legal matter. Physical evidence does not provide information which proves that something is so or not so, or that something is yes or no. That is, we cannot make binary decision like this, black and white. We cannot make a decision like this, but we have like rather a continuous grading of gray levels. That is, that the opinion is not deterministic, yes or no approach, but it needs to be followed a probabilistic approach. And the value of the physical evidence, strength of that physical evidence lies between two extremes of yes or no. Right. So also in a trial, now all should, I hope everyone understands this, that in a trial, the defendant is assumed innocent till proved guilty. The burden of proof lies on the prosecution. The prosecution presents evidence against the defendant of his involvement in the crime, and the court evaluates the evidence and pronounces the verdict of guilty or not guilty. If the evidence is strong enough to reject the assumption of innocence, the verdict is guilty. And if the evidence is not strong enough, then we reject the assumption of innocence and the verdict is not guilty. And when there is not just enough evidence, then there may be, this means that there is no, not just evidence to convict or to exonerate. So it all depends on how much evidence is there against the defendant and how the court evaluates this. So it is a lot of uncertainty is involved in all stages of evidence evaluation. So physical evidence is needed to be interpreted after laboratory examinations and it's most important. Interpretation is assessing and understanding the evidential value of the results or observations with regard to the context of the case. That is, the evidence is evaluated with regard to the context of the case. That is, the circumstances of the case. So, thus here in this interpretation of the physical evidence, statistics and probability are the reasoning and operating tools to describe and measure the uncertainties related to that. You also may be knowing that the definition of statistics, how statistics is defined. We say that uncertainty is there in almost all natural phenomena, and uncertainty is also there in forensic science. And statistics a way of quantifying this uncertainty. Statistics a way of quantifying the uncertainty. So we are here using statistics to quantify the uncertainty that is related to them. And you must understand, if there is uncertainty, then you cannot be perfectly certain about the opinion. This need for statistics and probability is not new. Way back in 1953, Paul Kirk stated that in the court of law, it is often not recognized that all identification is purely a matter of probability. This was stated in 1953 by Paul Kirk, that all identification is purely a matter of probability. And in another article, The Ontogeny of Criminalistics, he indicated, while it may be both correct and useful, too much room still exists for honest disagreement between witnesses. Witnesses can disagree. Much of this problem would be avoided if systematic study were devoted to the development of sound probability considerations applied to the evidence interpretation and also to the areas in which statistical analysis could properly contribute to correct evaluations. So, I hope this makes the case for the use of statistics stronger with a statement by Paul Kirk that statistics is very important in the interpretation of physical evidence. Recent times have seen the review of forensic profession all over the world. And you must be aware of the report of the National Academies of Sciences entitled The Strengthening Forensic Science in the United States, The Path Forward. This report was mandated by the US Senate, and the report came out in the year 2009. And this report states that the current practices of forensic science, as well as all the forensic disciplines, not including DNA, need to be revised, and this report gave 13 recommendations to improve the reliability of these techniques and in general to their contribution to the justice systems. And it may be mentioned that this report acknowledges the lack of statistical foundation in the various examinations of various types of physical evidence, but still they found that examiners make probabilistic claims based on their experience. A probabilistic claim made on the experience is not desirable. We need firm statistical foundations to make such claims. This report further states, and very strangely, that current forensic science system is not based on science. This analysis is frequently subjective. That is, when we try to interpret evidence, then our interpretation tends to be subjective. When it is subjective, then it cannot be demonstrated. Only when it is objective, then it can be demonstrated and its reliability can be known. Subjective decision making does not stand the test of that is imposed nowadays. And this report says the same technique used by the same analyst on the same sample can lead even to a different results. And still, the experts in their core presences, in my training, knowledge, and experience, they state their evidence like this. According to my training, knowledge, and experience, my opinion is this. Whereas it should be objective. And this report further states that there is a lot we do not know about other forensic disciplines except DNA. I may mention here that DNA was not subjected to this criticism. Only the other identification sciences, like I mentioned, fingerprints, then firearms identification, and then fibers and shoe prints, like these comparative disciplines were examined, criticized. And this report says that considerably more research and development is needed to provide a rigorous evaluation of the capacity of a method to consistently and with a high degree of certainty demonstrate a connection between the evidence and a specific individual or source. So when we want to give an opinion with a high degree of certainty, then this means we need more research and development to achieve this. And this report also says that the practitioner of forensic science rely on human interpretations that could be tainted by error, the threat of bias, or the absence of sound operational procedures. That is, errors can be there can be bias, an expert can be biased. I will discuss the different types of biases later on. And this threat of bias was recognized in the MAS report also. Now we'll see the cognitive. What are the biases? Biases are cognitive biases and contextual biases. I'll just discuss these briefly. Cognitive bias, one type of cognitive bias is confirmation bias. The tendency to seek confirming rather than disconfirming evidence is called confirmation bias. Suppose if you are given some information when submitting the evidence, you are told that this evidence comes from the suspect and this comes from the crime scene, and this may influence your opinion in the matter. And if you have already a belief and you will try to confirm that belief, if the information is ambiguous, then this bias can influence the decision you make arrive at. And then there is also a tendency to recall confirming evidence in a biased manner, right? And further, there is a tendency to interpret the ambiguous evidence in manner that confirms pre-existing beliefs. You can read a lot about bias and its effect on experts, forensic experts. Dr. Itil Rohr is a cognitive neuroscientist, and he has published a lot of papers on bias and its effect on forensic practitioners. So you can search these cognitive and contextual bias and know a lot about, know further about these types of biases. Then another thing I want to talk about is role effects. Because in India, most of the forensic laboratories, they work under the police department, and the forensic practitioners, they try to side with the police. That is, they work for the police. So they may be influenced in their decision by the fact they are working for the police. And there is also the world over, many laboratories are under the police, but this is one of the risks, that the forensic experts may get influenced by the role they are playing, what they think their role is. If they think that they are independent witnesses, they are not neither for the prosecution nor for the defense. If they are independent, then it's okay. But if they think that we are working for the police and we have to prosecute the person, then it may affect their judgment. Then another type of bias is contextual bias. In contextual bias, what we mean by contextual bias is that when extraneous information related to the case is provided to the expert, like background of the case or the circumstances or the stories of the case, then this non-relevant information will hinder the objective work on the examination of the physical evidence. You may not work objectively and scientifically and you may be affected by this contextual bias. That is, any information, background information that should not be there, it may influence your decision. Further, I will talk about the Innocence Project. You can go to this site, www.innocenceproject.org, and then this is a non-government organization, and they are working on reviewing the past convictions in light of the DNA evidence. And they have found that reviewed about more than 350 cases, and where the convictions were set aside and the persons were released from prison. And it was found that about half of these Innocence Project cases involved unreliable or improper forensic science. And now it is recognized that the scientific technique of bite mark comparison is now thought to be subjective. And the forensic science techniques also lack uniform scientific standards. You can see this in graphical form, that forensic science was responsible for half of these wrongful convictions. And this wrongful conviction has two phases. One is improper testimony, and the other is proper testimony. Proper testimony but wrong techniques. So improper testimony means they have exaggerated their claims about the evidence. So this is the state of affairs. Does it mean that all forensic science evidence is not useful and inadmissible? No, it does not mean, it does not question all the forensic science, but it just says that forensic science is not infallible and forensic science has limits that should not be exceeded. We should recognize the limits of forensic science, and we should not say that it is infallible. And then the Daubert standard of admissibility requires testability of the technique, and it also requires that the error rates involved in the examination technique should also be known. Then peer review and publications and journal acceptance. Error rates are important in terms of the use of statistics, because error rates in a technique can be found by using the statistical methods. It's a prerequisite for finding the error rates. Error rates refer to the number of errors observed during the application of a given technique for a defined number of trials under controlled conditions. It is wrong to say that so and so technique is error free. It is never the case. Every technique has some error, but we should acknowledge the error and we should try to reduce the error. If one says that there is no error in his technique, it is wrong. And so we must find error rates of a technique also. And we should also make efforts to objectively quantify the limitations of the techniques as well as the risks that an error occurs. And statistical methods and probabilistic models are methods to accomplish such an endeavor. That is, we can find out the error rates using statistics and probability. So, how can statistics be used in forensic science? Statistics is used in R&D, in the development and validation of methods. For example, when you calibrate some method, then regression is used, linear regression will be used, and then when you find the errors also, that is uncertainties also, there also you need statistics. Then statistics can also be used during the development of databases and the interpretation of association of evidence with these databases. I will also discuss these things in the later parts. And statistics, most important is statistics is used to evaluate evidence. What do you mean by evaluation of evidence? Like I told you earlier, that it is not a yes or no situation. We should be giving the strength of evidence. And how do we find the strength of evidence? It is using the statistical methods. And I mentioned earlier that in the NAS report, DNA fingerprinting was not criticized because DNA has firm statistical foundations, and you must be knowing you must all be knowing this, that DNA has firm statistical foundations. And if we can involve statistics in other identification disciplines, we may also increase the individualizing capabilities of these techniques. Right. So this is how statistics can be used. And coming to evidence evaluation, we use statistics and probability in evaluating the evidence. And we test the hypothesis. The null hypothesis is, as I told earlier, that the accused is not involved. That is, innocence is assumed. The null hypothesis say the accused is not involved. Whereas the alternate hypothesis says the accused is involved. This means if we reject the null hypothesis, then the alternative hypothesis will be true and the person will be convicted. And how these hypotheses are involved, evaluated, this is evaluated by the use of probabilities. And then there is another term like likelihood ratio approach. Likelihood ratio. What this likelihood ratio is, this is the strength of the evidence. This is the likelihood ratio is the probability that probability of the evidence given that the null hypothesis is true versus the probability of the evidence given that the alternate hypothesis is true. So we will see an example how this likelihood ratio can be calculated. So in nutshell, likelihood ratio is helpful in giving strength of the evidence to evaluate the hypothesis. So this is the definition of likelihood ratio. This is probability of evidence given this vertical bar says this is a conditional probability of evidence given the same source or the suspect hypothesis, and divided by the probability of evidence given the different source or the some other person hypothesis. So this is how the likelihood ratio is evaluated. And when we evaluate the likelihood ratio, it comes further that it is not just similarity that should be that we should focus on for the evaluation of evidence, but we should also see typicality, how typical that evidence is in the general population. Here in this previous definition, this numerator is the similarity term and this denominator is the typicality term. How typical is this evidence in the general population? So we compare the degree of similarity between the samples and also the degree of typicality with respect to the relevant population. What is relevant population? We will also define this later on. This way. These are two. This is a graph for showing the likelihood ratio calculation for comparing when you compare the fundamental frequency of a known speaker and the general population. Now this is the variation. This blue curve shows the variation of the fundamental frequency for that suspect, and this red curve gives the variation of the fundamental frequency in the general population. You see that the red curve is has a larger extent than the blue curve. It is naturally so. And if we have a questioned voice sample, and for that we find the fundamental frequency, then we evaluate the probability. Actually, suppose the blue curve tells you is the known speaker model and red curve is the background speaker model. And this green value here, this is the question fundamental frequency. Now we will want to know whether this question value is more likely to come from the suspect or from the general population. So we evaluate at this point, we evaluate the probability, we find out the probability here, and this comes out to be 0.0066. Whereas for the general population at the same frequency, the probability value is 0.0058. This means the likelihood ratio, that is a ratio of this height, and this height. This is 11.35. That is, we can say that the suspect is 11.35 times more likely to have said these words, the question words, than any other person in the general relevant population. And suppose this was the case when the question frequency, this fundamental frequency was on a higher side, that is close to 180. Had it been somewhere here, somewhere around 120, then what would have been the likelihood ratio? first you would calculate the probability at this point for the same suspect model, and it will come out to be something like 0.0025, say. And when for the general population, you find out the probability, and here it will come out to be, say, let us say 0.012. Then the likelihood, what would be the likelihood ratio? It will be 0.00, half of this, 0.0025 divided by 0.012. Naturally, it is less than 1. So when the likelihood ratio is less than 1, then the different speaker hypothesis is favored. When the likelihood ratio is greater than 1, then the same speaker known hypothesis is favored. So depending on the value of likelihood ratio. This I have illustrated you how we can find out the likelihood ratio by using the probability distributions of the known speaker model and the population model. So this ends our first part of this session, and we have discussed the importance of statistics in the practice of forensic science, and we have also understood that statistics is needed to give a firm footing to the scientific interpretation of evidence. Now, what is statistics? Now we'll come to the basics of statistics. Statistics is the science of collecting, analyzing, and interpreting data, whose goal is to acquire understanding from them. That is, data does not convey anything unless it is interpreted, and the science of collecting, analyzing, and interpreting data is statistics. And you can make sense of data, that is huge data that is there. Sometimes now we talk about big data. A lot of data is there, but you need statistical technique to make insights into the data. And this data, first thing is, there are two types of statistics that are performed in the data. One is descriptive statistics, and the other is inferential statistics. Descriptive statistics is data observed from sampled population. You cannot examine all the population. You take a sample from the population, and the data observed for the sampled population can be summarized using numbers, tables, or graphs for the purpose of describing the data. We will describe some data later on. This is called descriptive statistics. But when we make inferences from that sample and the statistics from the sample about the general population, then this is called inferential statistics. Like we hear of exit polls. Exit polls do not take the opinion from each and every person that voted in the poll. They take a sample, and then after that, based on the statistics of that sample, they make inferences about the whole population, that the whole population of the voters. So this will be inferential statistics. We will be discussing the descriptive statistics as well as the inferential statistics. And inferential statistics also deals between the study with the study of the relationship between data, that is correlation and regression. So that is also one part of inferential statistics. Then I would like to also briefly mention the Bayes theorem. Bayes theorem is helpful in evaluating the evidence, and we use the likelihood ratio in the Bayes theorem. Bayes theorem says that the prior odds multiplied by the likelihood ratio give the posterior odds. That the prior beliefs are there. That is circumstantial evidence. Then you independently examine the evidence that is submitted to the laboratory. You give the strength of evidence in terms of likelihood ratio, and multiplying that likelihood ratio with the prior odds will give the posterior odds for that evidence. And this is the definition of the Bayes theorem. And this is the probability of suspect hypothesis, probability of different hypothesis. This is probability of evidence given the suspect hypothesis is true, and this is probability of evidence given the different person hypothesis is true. And then here you see this, there is a difference between these two. This is probability of the hypothesis given the evidence, and this is probability of the other hypothesis given the evidence. There is a difference between this. This is probability of evidence given the hypothesis, whereas this is probability of evidence given the probability of hypothesis given the evidence. So you must understand this. This is how we arrive at the evaluation of evidence. So now we talk about variables, samples, and populations. Statistics involve the study of a set of equivalent objects from which some characteristics, attributes, or features are observed. This is a set of equivalent objects. Like say, we gather data about different persons. We gather data about different persons, and we tabulate the various features. Like in an anthropology problem, we for every person we measure the height of the person, the length of the long bones, or the foot length, or the hand length, and we tabulate this. These are characteristics, attributes of the features, and these are called variables. All these this hand length, or their height, their foot length, this is called a variable. And then we come to population and individuals. Population is the whole population, whereas if we take a sample, the objects forming the population are called individuals, and the statistics exploit the properties of the populations, and variability is there in the population always. There is a difference between survey and census. Survey is a portion of the population under a study is called survey is the process of taking a sample from the portion of the population under study, right? So we for research purposes we always do surveys, and we take samples from the population, and we record the various variables of the individuals or the various instances of that case. So all variables, they can be categorized into numerical variables and categorical variables. Numerical variables are variables that involve numbers. They are continuous as well as discrete. Continuous variable can have any value, any possible value, like height of a person. Height of a person can be, say, 170.56 centimeters. It can have any value, decimal value, up to any limit of that resolution. It can have any value. So this variable is called a continuous variable. Whereas discrete variables have only discrete values, like 1, 2, 3, 4, like this. So these are discrete variables. Categorical variables, they don't generally involve numbers. These are labels. But these labels can be represented by numbers. But these numbers cannot be treated in the same way we use treat the numbers of the numerical variables. I will also discuss this later on. Categorical variables, there are two categories: regular categorical and ordinal. Regular categorical means there is no order in the categories. These are just 2 or 3 or 4 categories, like male and female. These are 2 categories. Yes or no, 2 categories. Or hot or cold, 2 categories. Like, but whereas in ordinal categorical variables, there is an order. Like one category is, and the other category can be put in order. Like if we say, if we evaluate the response of feedback of a survey, that how satisfied are you with the service, then dissatisfied, neutral, satisfied, very satisfied, or to the other extreme, very dissatisfied. So thus we have a grading, that one category is better than the other, right? So these are called ordinal variables. Then variables are also associated or independent. When 2 variables show some connection with another, they are called associated variables. Like we do in anthropology, like the height of the person is associated with the foot length. That is, more the foot length, more the height of the person. So we can say that the foot length and the height of the person they are associated. And therefore, associated variables are also called dependent variables, and vice versa. But if 2 variables are not associated, that is, they don't show any relationship between them. That relationship means if one variable increases, the other will also increase, or one variable increases, the other will decrease. This is an association, positive or negative association. But if the change in one variable does not affect the other variable, then these variables are said to be independent. So there is no evident connection between the 2. These are said to be independent variables. So we will also be discussing the dependent and independent variables. Then this association between variables can be expressed in terms of correlation and contingency table. Correlation is used for numerical variables. When the 2 variables whose association we are studying, they are numerical variables, we use correlation. But for variables that are categorical variables, we use contingency tables. And contingency tables give the proportions of various variables, right? And for contingency table, the chi-square test is useful to know the association with the categorical data. We will also discuss in the next session. Now, how do we see the association between variables? Here on the left side, you see a correlation plot between density of glass and on the x-axis and refractive index of glass on the y-axis. And you can see that when the density of the glass increases, the refractive index also tends to increase. And you can fit a line on this data. It is not perfectly fitted, but you can fit a line, and there is a linear relationship between the density and the refractive index. This is called a correlation plot. And for categorical variable, we make a contingency table. For example, suppose if we have a problem in which we want to see if there is gender discrimination or not, then there are 2 categories, male and female, gender, and then whether they are promoted or not, promoted and not promoted. Then we here put the number of promoted cases in males and number of promoted in females, and number of not promoted in males and number not promoted in females. And then we can find out the relative percentage of promoted males. Here it is 0.875, and percentage of promoted females, that is 0.583. Now there is a difference. There is a difference between the percentage of males promoted and the percentage of females promoted, and we would like to see whether this difference is statistically significant, whether it is just by chance or is there a real association between the promotion and the gender of a person. So this is about statistics, the various variables, and while using all these things, these concepts, the concept of probability also comes. Just a minute, please. The probability is a study of randomness and it tries to quantify the measurement of uncertainty. And probability of an event, as you all know, the proportion of times that an event occurs in many repeated trials of a random phenomena, where a random phenomena refers to an event whose outcome is uncertain. Like head and tail. Simply, if you give an example, then head and tail, tossing of a coin, we say the proportion of times that an event, suppose the coming up of head is an event, then what is the proportion that we toss a coin, how many times a head will come up? This is said to be 50%, 0.5. So 0.5 is the probability of a head's coming up, or similarly a tail's coming up. Right. So this is one definition of probability, and this is called the frequentist definition of probability. Frequentist definition is number of outcomes in E and total number of possible outcomes. They count the probability of any outcome of a random event is the proportion of times that the outcome would occur in a very long series of repetitions. The number of objects in a given category is called frequency for that category. And then we also have relative frequency and probability. One thing I want to mention is that probability denotes a long-term or long-run relative frequency. What I mean by this is this. That is, suppose you toss a coin, you say there is 50% probability of that coin coming head up, and you toss the coin, say 5 times. Then it may not exactly 6 times. It may not be 3 heads and 3 tails exactly. There may be difference. It may be 4 heads and 2 tails. It may be 5 heads and one tail. It may be all 6 heads. So this gap here between the actual and the theoretical is very large. This is very large. But when this number of trials is increased, this proportion of heads will tend to be equal to half. That is of the probability that is there. 0.5 was the probability, but this 0.5 probability will be achieved. That is, the proportion of heads will come to be half only after a very long series of trials. So this is what you call a long-term or long-run relative frequency. This is the concept of probability. Now there is another concept of Bayesian probability. Bayesian probability contains and expresses the degree of belief with respect to the outcome of a given event. There is a degree of belief associated with the outcome of the given event. That means the probabilities are conditional in the sense that assigning a probability for the occurrence of an event, information is required. Some information is required. Like, I give you an example. Suppose there is a tennis competition between 2 champions or 2 great players, say A and B, and there is an upcoming match between the 2. Then one way of predicting the outcome of the match would be to see the data, historical data, in the number of wins of each player. If one person is he had more number of wins, then would say more probability associated with that player, right? But another aspect can be there. This will be the frequentist probability. Another aspect is there. There are two types of courts. Say one is grass court and another is clay court. And you know that person A, the player A, is better at the clay courts, and the next match is going to be on the clay courts. Then the probability, the frequentist probability, will be defined by this background information. Will be altered by this background, this information, and this is what is involved in the Bayesian probabilities. So we will also take up this concept of Bayesian probability in a more detail. Now this is the last part of the session, and I will show you a case study, and I may mention that this case study appears in that book called Open Intro Statistics, and this is freely available under the Creative Commons license. And I have used these slides from that book and from that site. So this is a case study of gender discrimination. This study was said to be done in 1972 to assess whether gender discrimination is there in promotion matters. Right. 48 male bank supervisors were each given same personal file. They were given only single file, same file, identical file, but it was mentioned for 24 files, it was mentioned that the file belongs to a male, and for the other 24, it was mentioned that the file belongs to a female. And the bank supervisors were given the same personal file and were asked to judge whether the person should be promoted to a branch manager. And they were also told that this is a routine matter, routine promotion. So importantly, the files were identical except that half of the supervisors had files showing the person was a male, while the other half had files showing the person was a female. The files were identical, contents of the files were identical. So it was randomly determined which supervisor got male applications and which got female applications, randomly selected. And after this, out of the 48 files reviewed, 35 were promoted. 24 were said to be of males and 24 were said to be of females. And out of these 48 files, 35 files were promoted. Now this study was testing whether females are unfairly discriminated against or not. So how we can know this? Whether there is something going on, is there any gender discrimination, or it is just by chance? So this is an experiment in which random selection of the supervisors to get the male file or female file was done. So this is the data, and this data shows that out of the 24 male files, 21 were promoted and 3 were not promoted. But for female files, out of the 24, 14 were promoted and 10 were not promoted. We have created the contingency table here, and then we found what is the percentage of males promoted. It is 21 out of 24. So it comes out to be 0.875. And what is the percentage of females promoted? It is 14 divided by 24. That is 0.583. So do you see any association between gender of a person and the chances of his promotion or not promotion? It may appear that the number of females promoted the percentage of females promoted is larger than the percentage of females promoted. Sorry, what I said. Percentage of males promoted was larger by the percentage of females promoted by about 30%. So this difference can be real. This difference can be real, and there may be gender discrimination. But this difference can also be by chance. There is nothing going on. It just happened by chance. And now we will see that what is the likelihood of this happening just by chance, right? So we go further. There are two competing claims or two hypotheses. First is null hypothesis. There is nothing going on. This means promotion and gender are independent. No gender discrimination. The observed differences in proportion is simply by chance. This is the null hypothesis. Null hypothesis, you must be knowing, maintains the status quo. There is nothing going on. There is no association. This means promotion and gender are independent. Null hypothesis. But the other hypothesis is the alternate hypothesis. This is there is something going on. That is, promotion and gender are dependent. That is, there is a gender discrimination, and observed differences in proportion is not due to chance. This is the alternate hypothesis. Now we will see whether the null hypothesis is true or whether we reject the null hypothesis. We can see, we will see whether such differences can come just by chance, or is it not possible that they are just by chance. For this, we do a simulation. Very simple simulation. We take a deck of playing cards. You know, playing cards have 52 cards, and set aside the jokers, take out 3 aces. There are exactly 13 face cards, right? If we remove the aces, there are 13 face cards, 3 aces. We remove 3 aces, then we have 13 face cards. That is A, K, Q, and J. These are called face cards. And take out a number card, because there are 16 face cards and there are 36 number cards from 1 to 10. 36. 1 to 10. There are 36 number cards and there are 16 face cards. So you remove 3 aces so that you have 13 face cards. And then you remove 1 number card from the 36 number cards and you have 35 number cards. This means, sorry, 1 to not, it's not 1 to 10, but 2 to 10. 1 is ace. So we have done this because there were only 35 promotions and 13 rejections. So we made these numbers and then shuffle the cards and deal them. We have now 35 number cards and we have 13 face cards, and this matches the number of the promotions. Promoted, 35 are promoted and 13 are not promoted. So 13 represent the face cards and 35 represent the number cards. Then we mix these 48 cards, and then shuffle these cards and deal them into 2 groups of 24 size, because 24 males and 24 females. We deal them into 2 groups, and after that we count and record how many files in each groups are promoted, that is number cards. To calculate the proportion of promoted files in each group and take the difference, male minus female, and record this value, and repeat these steps 2 to 4. These steps, repeat this many times. So this is the scheme of things. 35 non-face cards and 13 face cards. And then in the first instance, when you deal these into 2 groups, you see that there are 18 promoted, that is 18 number cards out of 24, right? And in the other group, there are 17 promoted in the 24. So this percentage is 0.75 for the males and 0.708 for the females. What is the difference? This is 0.042, that is 4.2% is the difference. And this difference is due to chance. This is the difference that would be there if we assume that this difference is due to chance, only 4%. Then you repeat this a number of times. You repeat this a number of times, and then you will get a difference in proportions. If you repeat it, say 100, you make 100 simulations of this same thing. We did it by using number cards, but using computers, this can be done in a very short time. And if you do a large number of such simulations, then you will find that most of these differences will be close to the zero level. That is the probability of, now if we say this is the probability curve, the probability of the difference being close to zero will be highest if we assume that it is happening by chance. And as we go away from zero, we will see this probability decreasing both ways. So we saw that in that particular case, there was a 30% difference between the two proportions. 30% difference means somewhere here. So if we calculate the p-value here, what it comes out? This p-value will be very small. When p-value is very small, then we reject the null hypothesis and we say that the alternate hypothesis is true. That is, there is something going on. So what this simulated study showed, that there is a gender discrimination in the matters of promotion, because the differences that we observed in that study were not likely to have happened by chance. Had they happened by chance, then the difference would have been closer to zero. Here there is higher probability, but when we go away, this probability decreases, and depending on this probability value, we will make the p-value. When this p-value is very small, we reject the null hypothesis. So in this way, we can see that how do we test the hypothesis using probabilities. So we are towards the end of this session, and to recap this, we have discussed the uncertainty involved in scientific evidence, and then we also discussed what are the recent events where the forensic professional practice was reviewed. Then we talked about the cognitive and contextual biases and the lessons from Innocence Project. That is, half of the cases of wrongful conviction involved faulty forensic science. And then how statistics can be used. And then we knew about evidence evaluation and the likelihood ratios. Then we defined the samples, population and variables, association between variables, then defined probability, then took up the hypothesis testing using a case study. So this is the end of this first part of this three-part webinar series. And now if you have any questions, you can please ask.
Thank you, sir. Any participant, those who want to ask a question, they can raise their hand. I'll unmute them. Rishna Razak, please ask your question. Can you be a bit loud, Krishna, your voice is not coming. Any other participant? They want to ask a question? You can type your question also. Those who are on a YouTube live, they can type a question on YouTube. I'll take the question from there. So there is one question from the Anu Bhati. As mentioned, DNA fingerprinting is the statistically more reliable, but I would like to point out that they are subjected to error due to the quantity of DNA and technique used for the analysis.
Yes, that is true. That is true. And uh, this DNA examination is also problematic when DNA mixtures are considered. And as far as technique is there, it can have errors. But as far as interpretation of DNA evidence is concerned, it is more statistically grounded. This is what I want to say.
Any other participant have any question? Yes, Priyesh, you can unmute. Priyesh, yes, you can ask.
Hello, sir. Can
Yes.
you hear me? Hello,
Yes.
sir. I just wanted to ask if odds ratio and likelihood ratio are same or different. If it's same or
Sorry?
different. Is likelihood ratio similar to odds ratio, sir?
Odds ratio and likelihood ratio.
Yes, sir.
These are different things. And I will take up this in the next session. I will demonstrate how the odds ratio are different from the likelihood ratios. Yes, they are
Okay,
different.
sir. Thank you. Thank
In
you.
fact, they are odds ratios. They the definition of odds involves some other hypothesis, and the definition of likelihood ratio involves some other hypothesis.
Okay, sir. Thank you, sir.
Right? I will take up this in the next session also.
Yes, sir. Sure.
Yes, yes.
Any other participant? Thank you, sir. I'll request Sudhanshu to sum up the session.
Hello everyone. Thank you for your time and patience. I would like to thank Dr. Rajesh Verma for such an informative and interesting session. I hope that the number of participants would not decrease tomorrow and rather increase, as we had close to 1,000 registrations. So I request all the participants to be present tomorrow at the same time on the same platform. We'll be using the same meeting ID and the password, and Ranjit sir and me will be hosting the event. Thank you so much, everyone, especially Dr. Rajesh Verma sir. Thank you so much.
Thank you, Sudhanshuji. I also hope that tomorrow we will have some more practical things to share, and it will be more interesting tomorrow. Today it was just theoretical and background information. Tomorrow we will deal right away with practical aspects of statistics and their use in forensic science. Thank
To
you
all
very
the
much.
to all the viewers, I would just like to highlight that tomorrow sir will be covering linear regression and logistical regression and some data basics as well. So please be present, as tomorrow will be a much practical aspect of what we have learned today. Thank you so much, sir. Thank you, Ranjit sir, and everyone else. Thank you.
Thank you very much.